Hello. So this will be the lesson for section 6.3. I'm going to go ahead and skip the first page of notes. You can read through that yourself. It talks about row operations, which again will make more sense once we take a look at matrices, which we will do in chapter 7. I'm going to start on page 2. In this section, we are dealing with a system of equations that has 3 variables, so generally x, y, and z, and therefore 3 equations. Typically, however many variables you have is how many equations you need in order to produce a solution. Now there can be exceptions to that. Sometimes you can have cases where there's only 2 equations with 3 variables, and if that happens, then it's an unusual outcome of some kind. I guess we have the outcomes on the screen, so let's talk about those. So when you're dealing with a system, and I guess the other thing I should say about 6.3 is that these equations, while they have 3 variables, will always be linear equations. And while the word linear, it's a little misleading in this case because the graphs of these equations are not just lines anymore. They are the 3-dimensional equivalent of a line, which is a plane. A flat surface is what these graphs would look like, and they would exist in 3 dimensions, which would make them difficult to graph, and we're not going to be able to find the solutions by graphing unless we were going to use some kind of technology to help us graph in 3 dimensions. So we're not going to do that. So these are called linear equations. What's nice about that is that the variables are all raised to the first power. They're not multiplied together in any way. And so presumably these are the easiest kinds of system of equations involving 3 variables. In that situation where your system of equations are only linear equations, then one of the following 3 things would have to be true. Either there's exactly one solution, there are infinitely many solutions, or there is no solution at all. In the case I was referring to earlier, where if you have 3 variables but only 2 equations, it would be either 2 or 3. You can't have just one solution if you only have 2 equations with 3 variables. It would either have to be infinitely many solutions or no solution at all. I don't know if we'll see an example of that, but just a heads up in case you do run across something like that. So to solve a system of equations with 3 variables and 3 equations, it's a lot more work than when there's only 2 variables. One method of solving this type of system of equations when they're linear is that you can use matrices, which we will learn to do in chapter 7. But right now in 6.3, we are going to solve these by algebraically. And that really involves using the elimination method for the most part to whittle down the number of variables until you finally get down to 1 variable so that you can figure out what that variable is equal to. So this is the process that I like to follow. You can look at the previous page of notes to see how they went about working through that problem, but essentially the same idea. They manipulated the equations until finally they get 1 variable by itself, right? I'm going to try to do the same thing here, and I'm going to outline the steps that I typically follow in these situations. Now, you can make exceptions, and there is an exception that could be made here. In fact, it's hard to resist not making this exception because it'll make the problem a lot easier to solve. So we might just go ahead and use it. But I'll just go through my general process, and wherever you can find shortcuts, you should take those shortcuts, right? So I'm going to stand over here by the screen, so maybe I don't know how it's recording volume-wise, but hopefully you can hear me okay. All right. So first step is to use 2 equations to eliminate 1 variable. And I'll just spell out the word 1 instead of writing the number. Use 2 equations to eliminate 1 variable. This is very open-ended. You can use any 2 equations you would like, and you can eliminate any 1 variable that you would like. Because in general, this is the best you can hope for. When you're dealing with 2 equations, the most you can really hope to eliminate is 1 variable at a time. There are exceptions to that, which would again lead to shortcuts to this process. The shortcut in this situation is that we already have an equation of just two variables, which is the goal of step one. So the goal here is to end up with an equation of just two variables. Right, we want to get one out of the picture, and we want to have just one equation with two variables instead of three variables, an equation of two variables. So that's what you want to accomplish with step one. In general, it requires using two equations to eliminate one variable. But there are exceptions, which again are the shortcuts I'm talking about. And in this case, the shortcut is they've already given you an equation that fits that description, which is this equation right here. Right. Let me draw that again so that we can see all the numbers. So we already have an equation with just two variables, so we can use that as our conclusion for step one. We don't have to do any work in this case because the work has already been done for us. We already have an equation of just two variables, so that's what I will use for step one. Usually this shortcut's not available. Usually you'll have to do work to make something like that, but this time it's given to us. So I'm just going to use the third equation. So I'm going to label these equations. Let me use a different color here. A, B, and C. So we can just refer to them a little bit better. So I'm going to use equation C. As the result for step one. And so that will give me this equation here. I'll have 3x minus z equals 10. Again, this is a z right here. That's my outcome from step one. It was just given to me. I didn't have to do the actual work to produce that. Step two is to use a different pair of equations and eliminate the same variable. So using this equation for step one, the variable that's missing is the y, right? So y has been eliminated from this equation. Right, so keep that in mind. For step two, let me use a different color here. For step two, we have to use a different pair of equations to eliminate, sorry, I'm writing too fast evidently, to eliminate the same variable. Let me scroll down a little bit to eliminate the same variable. So for step two, I can't use the same combo of equations that I used in step one. Again, because we took a shortcut this time, I didn't actually use a combo of equations in step one. I just used equation C, right? So I can't use equation C again in step two because that's what I used as my result for step one. So this forces me to have to use, since it has to be a different pair of equations, I have to use A and B, right? I don't have a choice. I need to use those other two equations, and I have to eliminate the same variable, so that means I have to eliminate y. I don't have a choice this time. Y was eliminated from my equation in step one. I have to make y be the variable that I eliminate in step two. So going back up to the equations that we were given, we have to use A and B. So let's go ahead and do that over here in this empty space. For step two, I have to use equations A and B. X plus y plus z equals 7, and 2x minus y plus z equals 9. And I have to eliminate the y variable. It's not a choice this time. Because the goal of step two, which I'll write down here in just a minute, is to end up with a second equation that has the same two variables as the equation from step one. It has to be the same two variables. It has to be x and z in this particular example. And whoever created this equation, or this system of equations, I should say, was actually being rather generous because they've set these first two equations up so that it would be easiest to eliminate y. right? Sometimes that's not the case. Sometimes the variable you have to eliminate is one that you don't want to have to eliminate, right? Because it's a lot of work. But this time it's actually pretty straightforward. So the y's are already set up to cancel out. That's the one I want to have cancel out. So I can just go ahead and I hate when I do that. I can just go ahead and let me readjust that. Let me see if I can. I don't know if I can. See if I can go back this way. There we go. Okay, back here where we were before. Okay, let's try that one more time. I'm right on the border of my recording window, so I accidentally moved it. Apologize for that. We are going to add these two equations together because the y's are already set up to cancel out. And what we end up with is 3x plus 2z, right? The y's cancel out, equals 16. So that is the outcome from step 2, and it meets our goal of having a second equation with the same two variables as the first equation from step 1. Right? So that's the goal here. Let me go ahead and write that down for you. I know it's a lot of writing. But the goal here is to get a second equation with the same two variables as the equation from step 1. Hope that's legible enough, right? And we've accomplished our goal. Step 3 is to use the results from step 1 and 2 and solve them as a system of equations of two variables. So this gets pretty complicated. We are solving a system of equations within a system of equations, right? Step 3 is like an entire problem from the previous section, 6.2. We are solving a system of equations with two variables and two equations. Right? So step 3, solve the, how do I want to say this? I didn't word it this way before, sorry about that. Let me back up here a little bit. Use the equations from steps 1 and 2 and solve as a system of equations of two variables, right? Of equations of two variables. All right. So step 3, we'll go ahead and put that here in this empty space over here. Let's grab those two equations from step 1 and 2. From step 1, we had the equation 3x minus z equals 10. From step 2, we had the equation 3x plus 2z equals 16. We're going to put those two equations together and solve them as a system of equations. And so we want to use the techniques that we talked about over the last couple of sections for solving a system of equations of two variables. Let me make some room here to solve this. I'm going to use the elimination method, but you are more than welcome to try to use the substitution method or graphing if you really wanted to. I think those would be more challenging. This type of problem is most, how do I want to say this? Commonly, so this type of problem, elimination method is often the most viable option, right? I think while x looks like a good one to try to cancel out here using the elimination method, I would have to switch the sign of one of them to get them to cancel out. I kind of feel like just using z, because they're already opposite sign, even though it means I'll have to multiply by a number. Right? I feel like that's better than multiplying by a negative sign, but it's your preference, it's your call. I'm going to take the top equation here and multiply it by 2 on both sides, if I can squeeze that in there. And so I end up with 6x minus 2z equals 20. The bottom equation I will not modify, so I'm just going to copy that down. And then I will add these two equations together. And we end up with 9x equals 36, right, because the z's cancel out. We divide by 9 on both sides, and we get x is equal to 4, right? So let me keep that divider going. All right, so we finally got a value, right? So again, our whole goal here was to keep eliminating variables until we get down to just one variable, which we finally did. It happened to be x, and then we're able to solve for x, and we get x is equal to 4. Now that we know what x is equal to, a common mistake that students will make is they will want to take that number and plug it back into one of the original equations, but we actually don't want to go way back to the very beginning of the problem just yet. We want to finish what we started in step 3, which is let's finish solving that little mini system of equations. We got x, let's find z, right? We're not done extracting all the useful information out of this scenario just yet. We can get z out of this before we go back to the beginning of the problem, right? So I'm going to take x equals 4 and plug it back into one of these two equations here. Either one's fine. You should get the same answer either way. Since I'm going to be solving for z, again, I don't like having that negative sign in front of that z. So again, it's a matter of preference, but even though the numbers are bigger, I like that bottom equation a little bit more because all the numbers are positive, at least initially. So I'm going to plug it back into this bottom equation here. I'm going to plug 4 in for x, and then I can solve it for z. So let's go ahead and do that. We'll do that down here. Let me switch colors. So we'll have 3x plus 2z equals 16. I'm sorry, I'm trying to make my z's look like z's. We're going to plug 4 in for x here. And then we'll get 12. And now we can solve this for z. I'll subtract the 12 to the other side. Just going to scroll down a little bit further. We get 2z equals 4. We divide by 2 on both sides. We get z is equal to 2. That's still in step 3, right? We solved that system of equations with the equations we got from steps 1 and 2. Let me finish drawing this divider here. Now we're done with step 3. Now we move on to step 4, which is the final step. And that is plug the results from step 3 back into one of the original equations. To find the value of the remaining variable. In theory, you could use any equation that you want from the beginning, but in this case, there's one equation that just isn't going to work. So if we go scroll all the way back up to the beginning and look at all the work we've done up to that point, going back to the beginning of the problem, the bottom equation, equation C, is not viable here because it doesn't have a y variable, right? We have x, we have z. The last variable we need to find is y. I can't get that information from equation C, so don't use that one, right? So either use A or B. I'm thinking A looks a little more friendly, right? This equation looks a little bit nicer for solving for y. So I'm going to use equation A. I'm going to copy that down to the bottom of the screen, so keep it in mind. We have x plus y plus z equals 7. Let's go all the way back down here, and I think I'll just, I guess I'll finish over here where all the other work is, right? So step 4, we have x plus y plus z equals 7. We're going to plug in 4 for x. It's just off the screen. Let me scroll back up so you can see it. It's right there. We're going to plug in 4 for x, and we're going to plug in 2 for z, which is confusing because my z's look like 2, so I'm sorry about that. Whoops, scrolled the wrong way. And now we can solve for y, right? We'll have 4 for x, 2 for z, and now we can solve that for y. So we'll combine like terms. 4 plus 2 gives me 6. I'll subtract that 6 to the other side, and I get y is equal to 1. And finally, we solve the system of equations. So again, I warned you at the beginning, these problems are a little bit more challenging than if there's only two variables. There's a lot of drilling down to do here. My final answer, when you type this into WebAssign, will need to be as an ordered triple, which means you're going to put the three numbers together in such a way, as you see on the screen right now, in alphabetical order, right? So X has to go first. So X was 4, Y goes second, Y is 1, and then Z goes last, which was 2. So there's my solution. And again, we get one solution in this case. All right. All right, let's take a look at another example. This time, I'm not going to write the steps out in words. So we're going to follow the steps, but I'm not going to actually describe each one in writing. I'll verbally describe it for you. This time, we don't appear to have a shortcut like we did in the last example for step 1. So remember, step 1, we want to use two equations. So I guess I am going to write out some words here just so you can keep up with what's going on. To eliminate one variable, right? So we have to make a decision here. What two equations should we use? What variable do we want to eliminate? Keep in mind that whatever variable we choose here, we have to choose the same variable in step 2. So you really want to pick a variable that looks like it would be easy to eliminate twice, right? In two different scenarios. So I'm thinking Y or Z looks promising here. I feel like X doesn't really look like it'd be as easy to do. I don't know. X isn't so bad, I guess, but Y or Z looks a little bit more friendly to me. So you have to make a choice. If you were in class today, I would ask you to make the choice for me, but since I'm here by myself, I'll have to make the choice. And I'll do something different because last problem we eliminated Y. So let's eliminate Z this time. If I want to eliminate Z, what looks like the easiest way to do that? To me, it looks like using the first and the last equation. So if I label these A, B, and C, we're going to use equation A and C to eliminate Z. Right? And they're set up to eliminate immediately, right? So again, I chose Z on purpose. I chose those two equations on purpose because they were set up to eliminate right away. So it wouldn't take very much effort. And it looks like we're going to run into another shortcut in this problem. So we get 2x plus y minus z equals 7, and 3x minus y plus z equals 5. I chose these two equations because I wanted to eliminate z, but I get a bonus here, right? So I'm going to go ahead and add these equations together. The x's combine together. 2x plus 3x is 5x. The z's do cancel out, right? Which is what I was intending. But the y's also cancel out, so that's the bonus, right? We weren't expecting that. Usually, you can't expect that, right? It's uncommon for that to happen, right? The most you can hope to do intentionally is to eliminate one variable when you're working with two equations. When you can eliminate two, that's, like I said, that's a shortcut. That's a bonus. You can't rely on that always being an option. I wish you could, but that normally doesn't happen and normally isn't possible to happen. So while that's a nice bonus, I'm not really liking the other aspect of this problem because we're going to have to add the right-hand sides together and we get 12. And that's just not very nice to see, right? Because solving that for x, so since y and z are out of the picture, I only have x left. I can just go ahead and solve that for x. But it's going to be a fraction, right? That's the drawback here. So 12/5, unfortunately. Now maybe WebAssign's okay with you writing that as a decimal, and that's not a bad decimal. It's 2.4, but I'm going to leave it as a fraction. Okay. So that, again, kind of throws a wrench in our approach because we kind of skipped to step 3, right? We already have the value for one of our variables. So what we need to do is plug this information back in to one of the original equations, in fact, two of the original equations, but you have to use B at some point. So don't plug it back into A and C because A and C is what gave you x equals 12/5. It already knows, that combination already knows x is 12/5. If you do that, you end up getting the same equation twice, so it would be a waste of time. B has to contribute something here. So we have to plug this back into B to get some information out of B. But what's going to happen when we plug in x equals 12 fifths is we'll still have y and z remaining. And so I need two equations, right? If you have two variables, you need to have two equations to work with in order to get a solution out of it. So I need a second equation, so I can either choose A or C, right? I'll go ahead and choose A. And that'll give me a second equation, which will also have y and z after I plug in 12 fifths for x. And with two variables, we'll have those two equations that we can solve and get a solution out of that. So again, I have to be willing to improvise, right? Follow the steps I gave you on the previous problem as closely as you can, but look for shortcuts and improvise where necessary. Right? So I'm kind of not going to step 2 here because I don't need a step 2. I already have a part of my solution. So I'm going to plug it back into equation B. So let me keep that on the screen there. There's not enough room for everything. All right, so we're going to plug in, so I'm taking x minus 2y plus 2z equals negative 9. Make sure you catch that negative sign on the 9. We're going to plug 12 fifths in for x. So I'm going to get 12 fifths minus 2y plus 2z equals negative 9. Now, I'm not really wanting to do much more work here with that fraction tagging along. And so I'm going to get rid of that fraction by multiplying the common denominator to both sides, right? Which is 5. So I'll multiply 5 to both sides. When I distribute that 5 here, it'll cancel out with the 5 in the denominator, so I'll just get 12. But I have to multiply it to every other term, even though it's not a fraction, so I'll get minus 10y plus 10z equals negative 45, right? And then I can subtract the 12 to the other side, and I don't have to worry about dealing with a fraction, at least for the moment. Now, if another fraction might crop up at some point as I'm solving, but at least for now, we have some nice numbers to work with. So this will be negative 57, right, when we combine those together. Right. So this is from equation B. I have y and z here, two variables. So I need two equations to be able to solve for y and z, which is why we need to plug this back into one of the other equations. And I already chose A, so help me remember this. 2x plus y minus z equals 7. 2x plus z equal, I think that's what it was. Did I get the signs right? No, I got them backwards. Plus y minus z. Try that again. Okay, so 2x plus y minus z equals 7. Okay, I got it right. So we'll plug 12 fifths into this equation for x, and I'll get another equation with y and z. Right, so I'll have 2 times 12 fifths plus y minus z equals 7. That's going to be 24 fifths, right? If you think of the 2 as 2 over 1, 24 fifths. All right, and same thing as the previous situation. I don't really want to deal with that fraction, so I will multiply the common denominator to both sides. Think of that as 5 over 1 if you need to. The 5's cancel out. You get 24 plus 5y minus 5z equals 35. Then I'll subtract the 24 over, and now I have a second equation with the same two variables, right, as the first equation. So now I can try to solve this for y and z. Right, so here's what's going to happen. So I think we're going to have something interesting happen here. So let's put these two equations together. We have 10y negative 10y plus 10z equals negative 57. Here we have positive 5y minus 5z equals 11. I'm going to use the elimination method to solve this little mini system of equations. And I have to choose a variable to eliminate. So I will choose to eliminate z. Let's go for eliminating z again. That's what we tried to do the first time around. Excuse me. And so if I want z to cancel out, I need to make this into a 10, and I can do that by multiplying by 2. Right, so I'm going to multiply the bottom equation by 2, Sorry, I jumped down a little further than I wanted it to. All right, so the top equation stays the same. I'm just going to copy it down. The bottom equation, I'll get positive 10y minus 10z equals 22. And now I will add these two equations together. And the z's do cancel out, as I designed them to do, right? That was my intention all along. But unintentionally, the y's also cancel out. So this problem's just unusual all around, right? All the variables are gone, so that means on the left-hand side I have nothing left over. I have 0. On the right-hand side I have negative 25, right? Negative 25. I believe that's right, or is it 35? It's negative 35. Sorry, I can't do math. Negative 35. Either way, we draw the same conclusions. So if this ever happened at any point in solving a system of equations, if all your variables just disappear on you in the midst of solving the system of equations, and you get a statement from that that is not true, right? 0 does not equal negative 35, then that tells me this system of equations has no solution. Now, I went about doing this problem probably in the worst possible way. You might arrive at that conclusion sooner if you had approached it in a different way. So sometimes you'll find out on step 1 that there's no solution. Sometimes you'll find out on step 2, or sometimes you'll have to get an answer, plug it back, like what we did, right? We ended up making some progress. We got a value for x, but when we finally tried to drill down to y and z, we ended up finding there's actually no way to get all three equations to work together, right? X was cooperating, but y and z just did not cooperate, right? There's no y or z coordinate that will help us make all three equations true at the same time. So this system has no solution. If instead we end up getting 0 equals 0, which would be a true statement, that's the case where you have infinitely many solutions. I'm sorry, I'm doing a really bad job of writing that. Infinitely many solutions. And that requires a whole separate set of explanations, which may be what the next problem is about. So I'll save that for the next example, I think. So, all right. So let's move on to that next example. So I guess I'm kind of catching myself at the moment because my instinct was to say, are there any questions? But that's silly for me to ask when I'm in the room by myself. All right. So here's another system of equations. We're going to approach it in the same way, try to follow those same steps. We'll improvise where possible, right? Step 1, we'll try to do this, I'm assuming, because I don't know ahead of time that this problem is going to be unusual. I have a feeling this is going to be an example of infinitely many solutions, but I don't know that for sure. So I have to approach it as any other problem. And the first step for any normal system of equations of 3 variables is to use 2 equations, use blank and blank, to eliminate 1 variable. And I've never seen this problem. It's my first time looking at it, so I honestly don't know what to expect. We're discovering it together. All right, so I'll label my equations to make them easier to refer to. So let's just say A, B, and C. Taking stock of what these equations, and these are some pretty awful looking equations, aren't they? To me, it looks like the easiest one to build off of for eliminating a variable is going to be z, right? And the reason I say that is because z, and x maybe would be okay too. X actually is not a bad choice, but z is a little bit better because we have a blank z here. And I say blank, what I mean by that is the coefficient is a 1, so it's easy to build off of. I can make this z, I can put any number in front of it that I want. That makes it easy to eliminate with other z's, right? This x would also be easy to work with, but the big difference there is that that x is positive as well as all the other x's. So not only would I have to change the number in front of that x, I would have to change the sign. I'd have to make it negative as well, which isn't that hard to do, but it's an extra thing that you have to do. Whereas the z already has the opposite sign, right? That z is negative, the other z's are positive, so it has that extra thing going for it. So that's why I'm choosing to eliminate z. And I definitely want to use b as one of my equations because that's the easy one to build up to match any other number. And for the first equation, either one's fine. So I'll go with a. And if we make it to step 2, I would use c with b, right? To eliminate z again, if we get that far, right? And the only reason we wouldn't get that far is if this ends up having no solution or something unusual happens, right? So let's just see what happens. So I'm going to take equation A. Oh, you know what we could have done with this one too? Divided it by 3, right? If all the numbers are divisible by a common number, it's not a bad idea to reduce those numbers down by dividing through by that common number, right? So 3 is a common factor to all these. We could have divided by 3, but we'll just run with it. And then we have the second equation. All right. And then I'm going to change the bottom equation so that the z's will cancel out by multiplying by 6, right? That way I'll have a positive 6z on top, a negative 6z on the bottom. They'll cancel each other out. So I have to distribute it. So the top equation doesn't change, so I'm just going to copy that down. The bottom equation will get 6x plus 12y minus 6z equals 30. Make sure, you would be surprised, it's a very common mistake for students not to multiply the number to both sides of the equation, which is a very basic concept with equations, right? If you multiply 6 to one side, you have to multiply it to the other side. But in this scenario, students are so caught up on what's happening with x, y, and z that they often will overlook the right-hand side of the equation. So be careful not to do that, right? Make sure you multiply it to both sides. I'll add these equations together, right? And we will get 9x plus 9y. The z's cancel out, and we'll get 36, which, again, don't have to do this. It's not even always possible to do this, but because they all are divisible by 9, I can just make this equation just that much nicer to work with by dividing 9 on both sides, right? And so we end up with x plus y equals 4, right? It's a pretty basic, straightforward equation. All right, that 9 divides into both of them. All right, so that's step 1. Nothing unusual happened, right? I didn't get to solve, I can't solve it for x, I can't solve it for y because I still have 2 variables there, which means I'm moving on to step 2, right? Now step 2 is use a different pair of equations. So it's going to look the same as it did in step 1. Use blank and blank to eliminate the same variable. That's the thing I wanted to say was the same, right? Which I chose to eliminate z, right? I don't have a choice in step 2. If I chose to eliminate z in step 1, I have to eliminate z in step 2. Because my goal is to get a second equation with the same 2 variables as step 1. I want to have x and y. I want an equation with x and y, right? And that's it. To use a different pair of equations, we can't use the A-B combo again, right? I used the A-B combo in step 1. I can't use that same combo in step 2. So I either have to do A and C or B and C. And I already mentioned that B is our better option. It's easier to work with to eliminate Z. So I'm going to go with using B and C to eliminate Z again. So B is the same equation that we have up here. It's x plus 2y minus z equals 5, right? That's equation B. That's the easy one to build off of. Equation C is 5x minus 8y plus 13z. I don't know if I can remember this. 5x minus 8y plus 13z. And I think I remember that, okay? So let's just double check. 5x minus 8y, 13z equals 7. 5x, 5, negative 8, 13, 7. 13, 7. Okay, so we're good. All right. To eliminate z, I will need to multiply the top equation by 13. And that means I have to multiply it to both sides of the equation, distribute it all the way through. So I end up getting 13x plus 26y minus 13z equals 65, right? Because 13 times 5 would be 65, right? Yeah, I think that's right. The bottom equation I don't have to modify, so I'll just copy it down right underneath that. Plus 13z equals 7, right? And now I can add these two equations together, and I will get 18x plus 18y. The 13z's cancel out, equals 72. Right? And that equation can also be simplified. And it turns out, you might not really recognize it because it's not a common thing to work with, but 72, I believe, is divisible by 18. So check that in your calculator, and you are going to get, and I'm really not surprised to see this, the same equation we got in step 1, because it's happening exactly as I thought it would. So what's going to happen is now we can move on to step 3. Right? Remember what step 3 was from that first example? We want to take the two equations we got from step 1 and 2, right? So this is from step 1. I'm going to label it because it's confusing because we got the same thing from step 2, right? And this is from step 2. And if we wouldn't have divided by 9 or divided by 18, we wouldn't actually even maybe know that they're the same equation. But because we simplified them, we see they're exactly the same as one another. But step 3 is now try to solve this as a system of equations of two variables. And when I go to do that, I will try to eliminate, let's say we try to eliminate y. I can get y to cancel out by multiplying that bottom equation by -1. So the top equation stays the same. The bottom equation becomes -x minus y and -4. And when I go to add these two equations together, everything cancels out. Not just the left-hand side, not just the x's, not just the y's. The 4 does too, right? So I get 0 equals 0, and this is what I warned you about in the previous problem. This is true, which means we have infinitely many solutions. So if your variables cancel out and it's false, there's no solution. But if your variables cancel out and it's true, it's infinitely many solutions. So you have to really be on your toes because you couldn't really get more opposite than that, right? So you don't want to just kind of take a guess at which one it is, because if you guess wrong, you've guessed the worst, the most opposite answer you possibly could, right? So it's not just being wrong, you're as wrong as you could possibly get if you guess incorrectly here, right? So we have infinitely many solutions. Now, what's interesting about this is, when there's only two variables, it's kind of a dumb case because it just means you have the same equation twice. And you just kind of say something to that effect that, okay, it's whatever solves this equation, that's my solution set, right? And there's infinitely many things that solve that equation. But when there's three variables, it's actually a little more intricate than that. So what we do in this case, when there's infinitely many solutions, is you go back to that equation of two variables. Right? Because infinitely many solutions, don't confuse that with anything works. That's not the same thing. 0, 0, 0 is not a solution to this system of equations. If I plug in 0 for x and 0 for y and 0 for z, it doesn't work. It doesn't work in any of the equations. So infinite solutions doesn't mean anything is a solution. There's still restrictions on what works, but there's infinitely many things that will solve the equation, but we have to figure out what those infinitely many things are. And this helps me figure that out, right? So whatever is a solution to this system of equations, x plus y has to equal 4. So only ordered triples where the x and the y coordinate add up to 4 can be solutions to this system of equations. Right? So what we can do with that is we can solve that for either x or y. Now, WebAssign, I don't know if it's going to care how you format that. On paper, it doesn't matter which one you pick. WebAssign might say you have to put it in terms of x or put it in terms of y. So I'm just going to solve this I want to solve it for y because that just feels more natural to do, but I don't know, I'm afraid that WebAssign might want to say solve it for x or whatever. So I don't know. Let's solve it for y. Actually, I think that makes more sense because that puts the answers in terms of x. So I'll solve it for y. And I get y equals 4 minus x. So what that tells me, if I think about an ordered triple like this, I can plug this information into that. You can think of it like a formula. I can plug it into this formula here. So that the y-coordinate has to be 4 minus the x-coordinate. And that tells me that I can pick x to be whatever I want. There's where you get your infinity, right? I can pick x to be any number I want, but then the y-coordinate, you don't have a choice. The y-coordinate has to be 4 minus whatever the x-coordinate is. Now the question here is, well, what about the z-coordinate? What would that have to equal? So if I pick x equals, for example, if I pick x equals 1, this formula tells me that the y-coordinate would have to be 3. I don't have a choice there. If x is equal to 1, y has to equal 3. But what about the z-coordinate? Can it be whatever I want it to be, or is there a formula for calculating z? And it turns out there will be a formula for calculating z. And the way you get that is you have to plug this into one of the original equations. And solve for z in this case. Right, because that's what we're looking for. What does z have to equal? So I'm going to take y equals 4 minus x. So it's a substitution thing. I guess I said it's always elimination, but this will be the one exception to that. We're going to substitute that into one of the original equations. So I'm going to try to pick the easiest one. I really think the middle one seems like the nicer looking equation, right? X plus 2y minus z equals 5. So help me remember that. X plus 2y minus z. I'm saying help me remember, but you can't because you're not here. So we have x, I already forgot, plus 2y minus z equals 5. I think that's what it was. Just double check that one more time. X plus, so it's 1, 2, negative 1, 5. Right, 1, 2, negative 1. Okay, this is right. So we're going to plug our result here. Let me pick a different color. In for y, right? So we get x plus 2 times in place of y. We're going to plug in 4 minus x. We have minus z equals 5 still, so we copy that down. And I still have 2 variables lingering around, and that's the issue with this system of equations, is that you can't get away from that. No matter how you try to manipulate the equations, there's always going to be 2 variables hanging out, or you lose all of them, right? You can't narrow it down to just one variable. Right, but what we can do with this is that we can solve z in terms of x as well, right? So what we're going to do is distribute the 2. We get x plus, oh, why am I saying 2y? That's a 4. 8 minus 2x minus z equals 5, right? So I'm distributing the 2. I can combine the x's together, so I get 8 minus x minus z equals 5. And I suppose the easiest way to solve this is to add the z to the right-hand side, and then while we're at it, subtract the 5 over to the left-hand side. So we get 3 minus x is equal to z, right? So basically flip-flop the z and the 5, right? And then combine the 5 with the 8. And so the z-coordinate, again, can't just be any number I want. It's based on whatever I choose as the x-coordinate, right? So let's plug that back in up here, right? So let's just rewrite the whole thing, because I'm kind of out of room up there. So going back to this idea that our solution will have this form to it, we know the y-coordinate is going to be 4 minus whatever the x-coordinate is, and we just found out that the z-coordinate will be 3 minus whatever the x-coordinate is. But x is free. X can be any number we want to pick, and there's infinitely many numbers to pick, right? So we can generate an infinite number of solutions using this formula here. So this is what you would need to type into WebAssign as your solution set for this system of equations. And just understand that this means there are infinitely many solutions that can be generated. So one possible solution, for example, is if I pick x equals 1. Let's go back to that. I just plug in 1 up here, so I get 1, comma 3, comma 2. Right? So I'll get 4 minus 1, which is how I get 3, and then 3 minus 1 is going to give me 2. Right? I could pick x equals 5. Right? Again, x is free to pick. You can pick any number you want, and it will generate a solution. Right? And then I have 5, comma 4 minus 5 is negative 1, 3 minus 5 is negative 2. That's another solution. I could pick x equals 0, for example, and I will get 0. When I plug in 0 for x, I get 4 minus 0, which is 4. and 3 minus 0 for z, which is going to be 3. That's another solution. And I could just keep going, right? So these are just, here's 3 solutions, excuse me, to the system of equations. But I could just keep picking different numbers for x and creating more solutions, right? There's infinitely many. And all of them can be described using this formula right here. So that's how it works when there's infinitely many solutions, which again is the dependent system, right? It's dependent when there's infinitely many. Okay, so I paused my recording so that I could look through this last problem on the notes. It's a word problem. And since I'm already at the 50-minute mark for my recording, I thought I'd just go ahead and work out the problem ahead of time and then talk my way through my work in this video. I thought that might save us a little bit of time so we don't spend another 20 minutes on this video. So in this situation, we have an object that's being launched straight up into the air and then coming straight back down. Now this looks like it's kind of moving over a little bit if you look at the graphic, but I really think that this formula applies to an object that's going straight up and coming straight back down. And that formula that describes that kind of situation is s equals 1/2 at squared plus v sub 0 t plus s sub 0, where a is the acceleration due to gravity. That's the gravity pushing the ball back down to the ground or whatever the object is. V sub 0 is the initial velocity with which the ball is launched, and s sub 0 is the initial height at which the ball is launched. We're not given any of that information, so we don't know the acceleration, we don't know the initial velocity, we don't know the initial height. We are supposed to determine that from the points that are provided. So they give us 3 points in this problem, and they don't even give us the points as ordered pairs, but I took that information and set them up as ordered pairs here, right? So s is equal to 52 at t equals 1. So that means after 1 second, the object is at 52 feet, or whatever the units are. After 2 seconds, it's back at 52 feet. So what happened was it went up and then came back down, and it's back at 52 again. And after 3 seconds, it's at 20 feet, so it's kind of getting close to being back down on the ground, right? So I set those up as ordered pairs. Be careful, it's a little tricky here because the time should go first, right? T is your x coordinates, your independent variable. S is your dependent variable, so that should go second. So it's 1, 52, 2, 52, and 3, 20. What you're going to do with those 3 points is plug them into this formula. Now, what I did with the formula is I didn't like that fraction being there. I thought that was going to give me a hard time as I tried to solve the system of equations. So I multiplied both sides of that formula by 2 to make that 1/2 go away. So now my formula looks like this. Right? And into that formula, I plugged in these 3 points. So I plugged in 1, 52 into that formula, which is what you see here on the screen. I plugged in 2, 52 into that formula. And again, this is getting plugged in for s and for t. So even though those are our variables in this formula, we're actually plugging numbers into those variables. And what we're actually solving for is a v sub 0 and s sub 0. So in our system of equations, our variable is actually going to be a v sub 0 and s sub 0. It's not going to be t or s, right? So we plug in these 3 points into that formula. We get 3 separate equations with a, v sub 0, and s sub 0. So what I did with these 3 equations here is I cleaned them up a little bit, and this is what you end up getting, right? So simplify, 2 squared is equal to 4. That's how I get 4a right here, right? 2 times 2 gives me 4. That's how I get 4 times v sub 0. 2 times 52 is 104. So I simplified it, and I flipped it around the other way to put the 104 on the right-hand side. So do that with all 3 of those. Again, you can pause the video at any time to kind of take a closer look at the work. And this is what you end up with. So this is your system of equations that you're trying to solve. We'll go through the usual process that I outlined in the first example. Step 1, use 2 of these equations to eliminate 1 variable. I chose to use equations A and B to eliminate s sub 0 because if you look, as you're plugging these numbers into the formula, this never changes. It's 2 times s sub 0 all the way down. So that one's going to be pretty easy to eliminate because it's the same thing all the way through. So I chose to eliminate s sub 0. I just randomly picked A and B to do that with. And so I wrote A and B here. To get s sub 0 to cancel out, I'll multiply the top equation by -1. Right? and I end up getting this right here. The bottom equation stays the same, right? So this is what we get when we multiply by -1. This is what we, this one we don't change, so I just copied it down. I add those two equations together. The s sub zeros cancel out. A little bit weirdly, the 104's also cancel out, so I get 0 on the right-hand side, but that doesn't really mean anything in particular. My variables are still there, so it doesn't mean no solution. It doesn't mean infinitely many solutions. It just means you get 0 on the right-hand side. All right, that's step 1. Step 2, use a different pair of equations to eliminate the same variable. So I have to eliminate s sub 0 again, and I chose to use a and c to eliminate s sub 0. So again, here's equation A, here's equation C. I'll do the same thing I did in step 1 to get s sub 0 to cancel out. Multiply the top equation by -1. Right? So we get this. The bottom equation I don't have to modify, so I just copy it down. Add those two equations together, we get this result. S sub 0 cancels out, we end up getting this. So this is actually working out. There's nothing unusual about this problem. We're going to get a solution, and there's no shortcuts here either. So this actually really demonstrates how the typical problem should look for the system of equations. Step 3 is to take the results that we just got from step 1 and 2 and solve these as a system of equations. So I have to decide which variable I want to eliminate. I decided to try to eliminate v sub 0. I thought that'd be the easiest one to get rid of. And I can do that by multiplying the top equation by -2, which is how I got this result over here. Right, so -2 times 3a gives me -6a. -2 times 2v sub 0 gives me -4v sub 0. And then -2 times 0 is still just going to be 0. So that stays the same, which is kind of nice. The bottom equation I didn't modify, so I just copied it over here. I added these two equations together. The v sub 0's cancel out. I get 2a is equal to -64. I'm now able to solve for a, and I get a equals -32. If you're surprised that a is negative, it actually makes sense because this is actually the acceleration due to gravity, and gravity is pushing the ball back down. It's trying to lower the height of the ball. So when we throw the ball in the air, our efforts are trying to make the height bigger, but gravity's effort is to bring the height back down. So that's why the acceleration is negative. What we do with that information is we plug it back into one of the original equations. So I chose to plug it back into, not one of the original equations, excuse me, I misspoke. Plug it back into, oh, sorry about that, that was a big mistake. Plug that back into one of the equations from step 3, right? I don't want to go back to the very beginning, but one of the original equations in step 3. And so I decided to plug it into the top equation, and then I continued my work down here, right? So I'm plugging it in here for A, which gives me -32 here, and then I can solve for v sub 0, so that gives me -96. I add the 96 to the other side, and then I divide by 2, and I get v sub 0 is equal to 48. So that's the initial height, not the initial height, excuse me, keep speaking, because I'm trying to hurry. It's the initial velocity of the ball, or whatever the object is. That's how hard we threw it into the air, right? Now that I have v sub 0 and I have a, I move on to step 4, which is now to take those two numbers and plug it back into one of the original equations. I think equation A, I think that I use capital A here, so equation A would be the easiest one to work with. So I grabbed equation A. I'm going to plug in -32 for A, for the acceleration, and 48 for v sub 0, which is, you see I did here. And now I can simplify that and solve it for s sub 0, which is the initial height, right? So you can pause the video to, analyze my steps here a little bit closer if you'd like to do that. But there's the work right there, right? So now that I have a value for all three of these, I don't want to say metrics, I can't think of the right word to use there. But now that I have a value for all three of these things, I can go back to the original formula. This is before I multiplied it by 2 on both sides. You want to go back to the original and plug in the information that we just found, right? So we found that A is -32, V sub 0 is 48, and S sub 0, I didn't mention it, but we got 20 for that, right? When we solved that for S sub 0. And I can plug that into my formula, and then this can be simplified further. Half of -32 is going to be -16. And so this equation models that scenario, right? And we were able to figure out the initial velocity and the initial height of the ball, and we figured out the acceleration due to gravity by using those points that were provided at the beginning. And the punchline here is that given 3 points, you can always figure out a parabola. So, something I always like to point out to my students, it takes 2 points to define a line, right? If you want to graph a line, you need 2 points, right? 2 points will help you figure out the equation of a line. That's all you need is 2 points. It turns out, even though parabolas are a little bit more complicated looking, right? So a parabola looks like this. All you need are 3 random points from that parabola to determine what that parabola is. That 3 point, there's only one parabola that can pass through 3 given points. And 3 points will help you figure out the equation of a parabola, just like 2 points will help you figure out the equation of a line, right? So it only takes 3 points, even though to me it seems counterintuitive because parabolas are much more complicated. I would think you would need more information than that. But 3 points is all it takes to figure out what a parabola looks like or to figure out the equation of a parabola. And we just proved that with this example that we did right here. So anyway, sorry I went a little bit over on time, and I'm sorry I had to really run through that last example pretty quickly. I don't know that there's any word problems like this on the homework, but hopefully that example will help if there is. If there's not, it doesn't hurt to have done this example because this is like the only example where things worked out in the most normal way, where we had to go through all 4 steps in the usual way. So anyways, if you have any questions, please be sure to reach out to me and let me know, and I will see you guys in class next time.